Remember before that in order to get an estimate of the population proportion, P, we took samples of the population and calculated for each of those samples the sample proportion, P hat. And then we were able to create the sampling distribution of the sample proportions, P hat, and find a mean and a standard deviation for the sampling distribution of the sample proportions, which allowed us then to make inferences about the population proportion, P. Well, the sampling distribution of the sample mean is, as you might imagine, really similar, but instead of talking about a proportion, we're just talking about the mean. In other words, if we again take samples of the population and we calculate the mean of each sample, which we call mu sub x bar, and then we graph all of those means in a distribution, they're going to form the sampling distribution of the sample mean. And that distribution is going to show us how likely it is that we get a particular value for this sample mean. Now, this all revolves around the central limit theorem, which we often abbreviate as the CLT. The central limit theorem is hugely important to us in statistics because normally when we're dealing with distributions for a population, distributions aren't usually perfectly normal. They don't usually approximate that bell-shaped curve. They can be skewed to the left, they can be skewed to the right, they can be uniform, they can be all kinds of weird shapes that are non-normal. But the central limit theorem tells us that even when a population distribution, so the distribution for the population, is non-normal, its sampling distribution of the sample mean will be normal if we use a big enough sample. In order to be a normal distribution, though, we have to meet a few conditions, just like we did when we were finding the sampling distribution of the sample proportion. So the first one is that we have to have random samples when we're choosing samples out of the population. The second one is that we have to meet the independence condition, or the 10% rule. And again, we'll meet the independence condition if we're sampling with replacement. If we're sampling without replacement, then we just have to make sure that our sample size stays under 10% of the population. If we stay under that 10%, then our samples are small enough that it approximates independence. But either way, one way or the other, we have to meet that independence condition. And then the third one is that we need more than 30 samples. Now, this one has a couple of caveats to it as well. So if the distribution of the population is normal, so if the population is already normally distributed, then we can take a smaller number of samples if we want to, and the sampling distribution of the sample mean will still be normal. That's because the population distribution was already normal. But if the original population distribution is non-normal, then we have to take at least 30 samples in order for the central limit theorem to do its work, in order for the central limit theorem to turn the sampling distribution of the sample mean into a normal distribution, even though we started with a non-normal distribution. If we start with a left-skewed distribution and we use fewer than 30 samples, then the sampling distribution of the sample mean will also be left-skewed. If the original population distribution was right-skewed, and we use fewer than 30 samples, then the sampling distribution of the sample mean will also be right-skewed. So in order for the sampling distribution of the sample mean to be normal, we have to take at least 30 samples unless we already know that the original population distribution was normal. Now, if we meet those three conditions, then we will have a normally distributed sampling distribution of the sample mean, and then we can say that the mean of the sampling distribution of the sample mean will be the same as the mean of the population. So in other words, the mean of the sampling distribution will be equal to the original mean of the population. We also know that the standard error of the sampling distribution of the sample mean will be equal to the standard deviation of the original population divided by the square root of the sample size. So let's walk through an example together. Let's say that we have a soccer ball factory. We have a company that produces soccer balls. And as you can imagine, since this is a whole soccer ball factory, they make a lot of soccer balls. And they try to fill each soccer ball to 8.7 pounds per square inch of pressure. So when they fill it up with air, they try to fill it to a mean of 8.7 pounds per square inch. And they have a standard deviation of 0.4 pounds per square inch for all of their soccer balls. So we would call 8.7 mu, the mean of the original population, and we would call 0.4 the standard deviation of the original population. Now, the company's doing some quality assurance, and so they randomly select 25 soccer balls, and they're going to go ahead and check the pressure. And they want to know the probability that the mean amount of pressure in these balls is within 0.2 pounds per square inch of the population mean. So the first thing we need to do is check normality. And we were told in the problem that we took a random sample of 25 balls. So we can go ahead and assume that we've met that condition. And then when we took these 25 soccer balls, we sampled without replacement. We took 25 off of the line. We didn't put each one back every time we took it. So we're sampling without replacement. However, we can assume that since this is a soccer ball company making soccer balls in a soccer ball factory, that they make more than 250 soccer balls. So this is going to be under the 10% threshold, and we can go ahead and assume independence, even though we're sampling without replacement. While we're not taking more than 30 samples, we're only taking 25 soccer balls. Let's say we've been told in the problem that the pressure in the soccer balls is normally distributed. In other words, the original population is normally distributed because the pressure to which they fill each soccer ball follows a normal distribution with a mean of 8.7 and a standard deviation of 0.4. So we'll meet this condition as well, and now we can go about answering our probability question. We know that the mean of our sample is going to be equal to the mean of the original population, so our mean is going to be 8.7. The standard deviation of the sampling distribution is going to be equal to the original standard deviation, 0.4, standard deviation of the population, divided by the square root of our sample size, so the square root of 25. And we'll calculate that that is 0.08. Now, since we want to know the probability that our sample mean is within 0.2 of the population mean, we need to express 0.2 in terms of standard deviations. Well, we know that one standard deviation is 0.08. So if we take 0.2 divided by 0.08, we get 2.5, which means that, let's say we have this normal distribution here. We know the mean is 8.7. This is the sampling distribution of the sample mean. So our mean is 8.7. And then we know one standard deviation is 0.08. So if this is the mean here, then one standard deviation, 0.08, might be here. Two standard deviations, 0.16, might be here. And then 2.5 standard deviations is going to be right here. And then same thing on the low end. We'd have one standard deviation. This would be 0.08 from the mean of 8.7. And then if we go one more standard deviation of 0.08, now we're going to be 0.16 away from the mean. And then 2.5 standard deviations might be right here. So since we're 2.5 standard deviations away, this is a z-score of negative 2.5 and a z-score here of 2.5. So we're looking for the probability that our z-score here is between negative 2.5 and positive 2.5. And if we look up positive 2.5 in a z-table, we find 0.9938. If we look up negative 2.5 in a z-table, we find 0.0062. Of course, this 0.9938 is going to give us all of this area here, all the way up to a z-score of 2.5. The z-score of negative 2.5 is going to give us all of this area right here up to a z-score of negative 2.5. So in order to find the value we're interested in, which is all the area in between those two, this area right here, we just want to take the 0.9938 and then subtract out the 0.0062. That subtracts out this little lower tail, leaving us with just the area in the middle that we want. And that difference is 0.9876. And then if we round that to the nearest hundredth, approximately 0.99 or 99%. Which means that when we use these sampling conditions with the 25 soccer balls, that our sample mean has an approximately 99% chance of falling within 0.2 pounds per square inch of the population mean of 8.7 pounds per square inch.